Good evening, all of you. We'll start our session in 2-3 minutes. So we'll wait for some people to join. So welcome all of you. So this is our 11th session on the uh, course study guide in the organic retrosynthesis, a problem-solving approach. And in this course, from last few lectures, we were covering about the uh, the retrosynthetic synthetic problems which involve uh, the retrosynthesis problem which involve the asymmetric synthesis, and we have covered some examples which involve the asymmetric approach in the retrosynthesis. So this lecture onward, we're gonna see some combined problems on this retrosynthesis uh, course. So I would like to take the first problem. So we'll just revise the concept that we have studied uh, in this course from first session onward. Okay, so this is first problem for today's discussion. Uh, so in this example, you can see the here we have the target molecule, and if you try to do the retrosynthesis of this one, so the first step in the retrosynthesis is the functional group interconversion. So you can see this amine we can basically synthesize from this type of imine, right? So this is the amine to this imine. So this is the functional group interconversion. Then we can, if you look at here, so we can basically do the disconnection here, and we get the starting ketone and the aniline as a starting material. So so it involve retrosynthesis of this material involve the functional group inversion and the disconnection. So if you look at the linear synthesis, so how the linear synthesis look like, you can clearly see from this example. So the first step between this ketone and the amine. So basically, if you treat the amine with the ketone, it will form the imine. So it will be this N double bond C, and so these two group here, which has the spinel ring attached. So we have seen also seen some reagent used for the retrosynthesis. So in that particularly, we have covered the sodium cyanoborohydride reduction. So if you do the reduction of the of this imine with the sodium cyanoborohydride, so that's the NaBH3CN. So we can basically get the this our target molecule. So this is just linear synthesis for single two steps linear synthesis for this target molecule. In the similar manner, we'll take some more examples. So I will not spend too much time on explaining each and every example. I'll just show you here the example, and so it will just refresh the concept that we have studied in this course. Okay, so this is the second example. You can see here in this example, similar manner. Uh, so this compound, how we can synthesize this compound? So here, basically this approach we have used here, disconnection, and in this disconnection particularly, we did this CN bond cleavage. So we get the starting to materials. One is the amine and one is the aromatic chloride. So this aryl chloride basically is our starting material. Uh, So from this aryl chloride particularly, you can see we can further do the retrosynthesis. So this we can also synthesize from the this chloride, benzene, chlorobenzene. So this chlorobenzene just a is our starting material. And if you look at the linear synthesis of this chlorobenzene, so you can clearly see uh, upon this on this linear synthesis of this target molecule. So the first step, reaction between the chlorobenzene in the and the HNO3 in the H2SO4. So basically, nitro group gets attached on the ortho and para position. So we have added excess of the HNO3 and H2SO4. So we get this dinitro molecule. So intermediate to 1. So when you treat this intermediate with the isopropyl amine, so basically it's a CN coupling reaction. We can get our target molecule. So this is how the some different synthetic approach have been used for the synthesis of this material. In the last case also, we can potentially use similar approach. So on this chlorobenzene basically, so if you have the chlorobenzene and if you use this amine and do the coupling reaction, so we can basically get the formation of this our target material. So which coupling reaction is this? So does anyone have any guess? So so we have the amine here and the chloro compound here. So if you want to couple this amine to chloro, you can basically use the Ullmann coupling or Buchwald coupling. And there are also other coupling, copper catalyzed coupling reactions. So you can use that one. And I'd like to mention some example. If you have such fluoro, and if you want to couple these fluoro compound with this carbazole, so this reaction works very perfectly using just cesium carbonate in the DMF solvent at 140 degrees Celsius. So it gives the so if you have the here bromo, so it will selectively give the this compound, and this reaction yields almost more than 90% yield. So this is also one CN coupling reaction. So you can use this coupling reaction in your problems while solving your problem. The next example here is the simple based on the simple nucleophilic substitution reaction. So all the problem that I am taking here. So just to revise the all the concept that we have learned in the course rate synthesis. So we are taking some exam oriented problems right now because you may have gonna face the exam in they say in 2 to 3 weeks. So we can refer this PPT to make practice. So okay, so this is our target molecule. If you want to do the retrosynthesis of this one, so you can basically cleave this bond here, and it can be either from this alkyl chloride and this alcohol. So basically, this is just nucleophilic substitution reaction. So you can, if you want to do the linear synthesis, you can just do this SN2 reaction. You can get the target molecule. Then we have here the very similar example. So here you can see this is the target material. You can basically do the disconnection here, and we get these two static materials. So this is the nucleophile S minus. It can basically attack on these uh, carbon center leads to the elimination of this bromine, and we get this target molecule in the linear synthesis. So alkynes also acts as a actually the nucleophile. So I just give one example for alkyne act as a nucleophile. So this is the one example. So you can see here, if you just do the bond cleavage, uh, okay, as you mentioned in the chat box, facing issue with the synthesis process, where chirality is mentioned in the assignment. Okay, assignment will. Okay, I will take that one. Some assignment question from these assignment question also. Okay, look at this example first. So if you do the disconnection here, so basically get this nucleophile. So this C negative acts as a nucleophile. And if you look at the linear synthesis, if you have this terminal alkyne and on addition of butyl lithium, you can basically get this lithiated compound, and this lithium uh, so this will be Li positive and this C negative. So this alkyne whole can act as a nucleophile, and it can you can use this alkyne on whichever for this substitution reaction. So in this case, we have this alkyl bromide. So this negative can replace this bromine, and we can get such target molecule. So this is about linear synthesis problem. So if you look at the some more problems which are particularly, so this is one category of problems that I will take here first. So this center is more important. You may seen some many problem based on these centers, particularly the active methylene group here. So if you look at this compound, so if I just expand the structure of this one, so this is the CH2 double. So it has these two hydrogens. So this center particularly, these hydrogens are more acidic. So if you add any type of any uh, base on this one, we can basically get these anion here, and you can add whatever required group on this position. So let's say if I treat this with the R CH2 CH2 Br, so we can basically uh, get this alkyl part attached at this position. So what we get here, we can basically get this RCH2, this R attached here. So basically this functionality we have attached. If you want to further add further different in group, different groups. So let's say if you want to add this group in again another group also instead of this hydrogen. So we can treat it with first with the base. So we get such type of anion, and then again treat with this such alkyl bromide or any alkyl iodide or chloride also. So we can basically get this dye substitution, right? So like this. So basically, you can add such groups on this type of active methylene compound. And the problems which involve such active methylene group are you may have seen several times. Then another simple synthesis, sorry, the retrosynthesis is example here that I am going to mention, this one. So you may see the structures a little bigger, but the synthesis wise it's quite easy. So what we can do in this particular example, so the first disconnection goes here, sorry, the functional group interconversion, and on this one. So it basically comes from this ester. So this alcohol can be synthesized from this ester. So if you do reduction of this alcohol, you can basically get this sorry ester. If you do the reduction of this ester, we can basically get this alcohol. Then how to synthesize this intermediate? So basically, uh, so this is basically we can do disconnection at this position, and the two starting materials here. If you look at the linear synthesis for this one, then it will be more clear. So this is what the starting material we had, which is the aldehyde. If you treat this aldehyde with this amine, we can basically get the enamine. So basically our NH2, if you treat this with the uh, any aldehyde ketone like this, so we initially get this type of compound. But if you, in this case particularly, so if you just look at this example, so if you abstract in terms of see this amine itself is basic, so we can basically get such enamine. So basically, uh, like this, right? So this is the imine and this is the enamine. So amine plus alkene. So we can get basically enamine from this one. And when we treat this enamine with these uh, alpha beta unsaturated ester, so we are basically this lone pair on nitrogen goes here. So the negative charge attack from this position on this beta position we can get here. This negative charge here stabilize, and basically we get such linear chain. And upon further hydrolysis, because in between the intermediate form, which will be the then imine intermediate. I will write the part which comes from the this aldehyde in this fashion. Right. So this is the newly formed bond. We get the anion at this position, and which is obviously abstract the proton from the solvent. And upon workup, uh, so basically this entire imine get back converted into the corresponding aldehyde. So we get this aldehyde back. Any doubt in this example? So we can able to get this one. And later, if you do the uh, lithium reduction with this lithium hydroxide, LiLH4. So we can do the LiLH4 to corresponding alcohols. So this all reducing agent we have already covered in one of our video. So the reducing agent we have seen in earlier case also this sodium cyanoborohydride. Yeah, sodium cyanoborohydride, and in this case this lithium aluminum hydride. So this is how we can do the retrosynthesis of this material. So someone mentioned the some assignment question from the some question from the assignment number 12. I will check the what are these questions. So in meantime, you can refer this example. We'll roughly discuss these questions from the assignment number 12. The first one is the bromination of these compound. So the following scheme major product. So if you look at the reaction of Br2 on this starting material, so I think in the starting they have forgot to mention the double bond in the structure. So I'm not sure how this reaction work without double bond because there should be a double bond there. Am I right? Because otherwise the reaction will not gonna work on the only this ketone. So if you have such only starting material and if you treat this with the bromine in THF and particularly at let's say 10 degrees Celsius, the reaction doesn't work, doesn't go anywhere. So in this case particularly, if we have the double bond here, so in that case we can basically solve this question. Okay, so let's say we have the starting material that I have mentioned. So this is our starting material, one with one methyl on the downside and another methyl on the upside. And the bromination reaction. So Br2, basically this bromine react with the alkene in this fashion. So one of the bromine form a bond here and this Br negative get eliminated. So initially the first step is formation of such bromine bond and this make is in plane. So in this case, so this bromine will be in plane. If I just show in this example itself, because there is no direct polarization in the bromine, so it will be delta positive and the delta negative. So the this olefin is electron rich. So this bond basically uh, push the electron density to the one of the bromine atom and then the charge polarization occur. So this Br negative then eliminated and we get the intermediate like this. So in this case, stereochemistry of methyl doesn't matter. So what we get? We get this intermediate. Then the another incoming electrophile, basically, sorry, the nucleophile Br negative attacks on the another position. Let's say here, this goes on the opposite direction. So overall, what we get? We are basically get this, let's say this dotted methyl. I will draw the stereochemistry. This methyl and this methyl here. The ketone remain there. One of the bromine will be attached here, another bromine will be here. Mm, however, in the if you look at the stereochemistry of these bromines, so they should be anti to each other. So in this case, either this product is formed or the another possibility. So this is the product. The stereochemistry between the bromine A and the bromine B, if you look at the stereochemistry here, this should be anti. So in this case, if you look at in these two, there are two possible structures. So in one, bromine here, bromine like this remaining structure will be the same. And in the other case, bromine and this bromine. So basically, this is the combination of these two. So this is what the product here. The next question is reaction of this starting material. This is the diol, so which is CH2OH. This is alcohol. We have the this tosyl group. So basically, this diol, what it does, it react with these, particularly the ketone. So it forms like this intermediate. So the first step is like this. The next one, we have the catalytic acid, so that assists the formation of this ketone. Then we have the, this is PHH, it's which is directly basically the benzene. So, and the reflux. So there is no any other steps in all. This is basically this benzene, which is non-reactive. So I don't think it has any reactivity here. So this is just a solvent. This catalytic acid we need to add to protect this, basically this ketone part. So if you have the ketone, the protection of this ketone we do generally do with the diol. So this 1,2-diol is added to protect this ketone basically only. So that's what we did, and we get this B product. So it is there is no any other steps involved in the in this case. Next here is the, I'm not sure why what is the purpose of giving such questions here in the assignment. So they are just like, the next question is much more similar. So we have this basically the product. I think this is the product of the last reaction. Yeah. So this is our starting material now. Okay. And if you react this with the potassium plus OT butyl, so basically this third butyl is uh sorry, O minus and K plus. So this is our nucleophile in the DMSO solvent. So what happened? So this is the negatively charged. So it can basically attack on this bromine to substitute this one. So obviously, this is the okay, sorry. In this case, it's not only the possibility of only substitution reaction. So this is electrophile, you can say. We also need to think out of the box. So in this case, what happened? So we can not directly simply do elimination on addition of these nucleophiles. So in this case, particularly this group, so negatively charged oxygen. So what one can do, one can simply just do the elimination reaction, sorry, substitution reaction here and get this product. The other possibility here is the, since this third butyl group is quite bulkier, so what it can do, it can basically abstract the proton present here. So this proton it can abstract. So this hydrogen. So this base basically abstract this proton, and this elimination reaction occurs. So we get this elimination, this product like this. So this, so these are the two possibility. Now you need to think of which is the more feasible product. So anyone have any guess here? So basically, uh, because of the bulkier third butyl group, the elimination reaction occurs dominantly because nucleophilic attack on such sterically hindered site, in this case, this sterically hindered site is not that feasible. So the proton abstraction followed by the elimination reaction occurs. So C product is the correct answer. Similar manner, we have the same question, very similar question based on the same similar subset. So basically, we did the reaction of this. This is the pH double bond O again double bond O pH. So basically, this is the anhydride and NBS is the N-bromosuccinylate, which is the source of electrophilic bromine. Okay, so how the reaction on this olefin occurs? We have the CCl4 as a solvent and the reflux. So here in this case, this is our starting olefin. So if you look at here, this anhydride is more reactive towards this olefin. So basically, so the negatively charged attack on the this electrophilic center and this negative charge go there. So basically, it forms double bond O pH. And similarly, this O negative basically uh, can attack here to get the product that we can get in this case will be either like this. But we have another source Br positive. Then what is its role? So mostly looking at the answers. So definitely this reaction does not go in this fashion. So if you look at the other possibilities, then by taking only account this electrophilic bromine, Br usually comes from this NBS. So it will definitely then in that case instead of these two electrophiles, so this first an electrophile and the another nucleophile, which is just fragment of this electrophile that we were earlier think. Instead of getting this, we can get basically so the one the answer A. So does anyone have any other possibility in their mind?
I think it's D.
To get the D product actually. So what are the options for how to get the D? So we have the olefin and this one. So there is no any some sort of to try to further get into more detail of the mechanism to get, let's say, the answer D. How we can go up to there? Because we don't have the equivalence of this one, whether it is catalytic or this NBS is catalytic.
This is radical mechanism I get because this is the par acid have been used, then NBS. I think allylic position going to be brominated. That's why D is. I am telling D.
Okay, so as you mentioning the radical mechanism with the peroxide, but if you look at the radical mechanism, so on this olefin, so we have the Br radical, let's say, it will goes to where? So because more reactive site is this olefin center is more reactive towards because it is the electron rich site. So let's say first electron goes here, so the first bromine can goes here then, and we get one radical at this position. So I need to look into the answer for this one because if you go by radical mechanism, then also how the reaction occur in at the center. Uh, okay, so the one that you are mentioning, the center, allylic center. So basically, how it can be possible in that way. So I think it's like this. So let's say we have this olefin. Uh, this CH bond is forms the radical first, then which is a stable radical because of this proton. Is it like this? And then when it react with this Br radical, then it can lead to the formation of this Br and H.
Yeah, like this probably. I'm thinking so.
Mm, we still need to check the actual accurate answer for this one. So
Yeah.
how the mechanism go? Because we are the organic chemist, we need to identify the mechanism behind each and every step. So as of now, just looking at the answers in the assignment. So answer D is the correct answer actually, but the mechanism may be then as shown here in the red one because the next question has the same starting material as I got the answer. That's as we got as you mentioned the answer option D. So that's the one. So basically the assignment is series of all questions just broke down into the shorter version. Okay, the next reaction on the product what we got here in the question as you mentioned answer D by using such maybe such mechanism. So okay, we have this starting and if you perform this reaction Hg acetate in diethyl ether at room temperature. So what will be the product here? So in this case, this is the source of OAC negative, right? So what is the correct answer here? Reaction of the olefin with the acetate. So it can show either reaction with this double bond or also with this bromine. Uh, it is this one But this hydroxide, so I believe this answer C is the one. At this position, OAC negative attacks here. This one goes here and the bromine negative get eliminated. So we initially it should get OAC. Then we still have the OAC negative. So which can be further on reaction either on the centers. So reaction of olefin with these generally with the silver acetate give the diacetylation generally. So I'm not sure whether the option C is correct or the B. So I think the option B is the one. Mainly this is the mechanism. So in this case, we don't have any NaOH, sorry, NaBH4. So as you mentioned, it should not directly go to the hydroxide as you can see here. So mainly these acetate is the source of nucleophile in our case because we don't have any water present in the reaction. And the solvent is diethyl ether. So other source of nucleophile, we don't have any other than the acetate. So the olefin react with the silver center, sorry, Hg center like this. So we have now, we don't have this water, so we have only acetate. So this attacks on this double bond. So the first step goes like this. The second step also, we don't have the water. So this entire Hg plus OAC group get eliminated by the addition of a second molecule of OAC. And in our case, we have the uh, bromine center, so which is also eliminated in this fashion in the very early stage. So the first step, as if you go by a mechanism, so we have the bromine here. So initially this Hg attacks here, then the OAC negative addition uh, across the center. So it will be this. The next one is similar attack of the OAC because there is no source of water other nucleophile. And the similar manner, third can also, sorry, the third OAC can also be eliminate this, sorry, substitute this bromine. So that's the possibility, I think. So therefore, the option B is more relevant to me. Okay, the next one is the The next question is the so this is the target, sorry, starting material we have and reaction of this target molecule with the NaOH and methanol. So basically the reduction of the keto center here because this ester functionality will be unreacted towards this NaBH4. So what we get? We get the alcohol there. However, in this case, the stereochemistry of alcohol is more important. So if you look closely at this alcohol center, you can clearly see this methyl substituent here directing upward. So obviously this entire ring will be the somewhat like this, right? Because this methyl is directing upward. So like this ketone, and I'll just write down all the structures. See, right? So like this. So if we look at, although we look, the first assumption here is the this bulkier methyl group is on the top side. So this hydride minus can attack from the bottom side, so as we can get this hydroxide directing upward. Uh, like, do you have any example? Another step is the mom protection, mom chloride protection. So basically, what we get. Okay, so it is much more clear if you look at the other options. So because of this methyl group, which is on the in the top side, so here we don't have the stereochemistry mentioned. So it can be either this hydrogen can be either on the top side or the bottom side. Okay, so if you look at these center here, this adjacent methyl group, sterically bulkier group, is present on very adjacent to this carbonyl group. So therefore, this hydride negative charge which attack on this carbon center from the backside. So hydrogen is attached on this carbon now will be on the backside. So this OH will be comes to on the top hand side. So because of this adjacent methyl group, the stereochemistry get induced. We get some selectivity in the stereochemistry, and we get the major product in which this hydroxy group is directing upward. The next step here on this one, once we get this hydroxide, we have this methyl, we call it as a mom chloride. When it treated this with the hydroxyl group, it will just do the protection of this hydroxy group. So we get the option B as a major product. And why I have neglected all other options? Mainly because this NaBH4 remain unreactive towards the, this is the ester. So it doesn't show any reactivity. So this is the first thing, the wrong option. Also, if you look at, okay, all other options, they have the similar manner. The last step that we have given here, this the protection, we have added just simple dipia. So in that case also there is no any possibility of this acetyl deprotection and further protection by this mom chloride. So therefore the option B here is the most correct option. Only if you focused on the stereochemistry, because of the backside attack happens on this carbon center due to presence of this methyl group on the beta side. So option B here is the correct option. If you look at the next question in the same series, Just a minute, I will just reshare the screen. Okay, if you look at the another question here, so which we know the reduction using the H2PDC and methanol. So where this H2PDC reduction occurs, so obviously it will directly occur on this olefin center. And if you have any CBZ protection in our group, then it can also replace that CBZ protection. But in our case, we have this only the reduction center, the double bond. So if you look at here, so here double bond is reduced. Here also double bond reduced. This H2PDC doesn't show any reaction towards the ketone. So the ketone should be retained. Also no any reaction towards this mom chloride, sorry, the MOM protection. So this is what the product we have here, the option C. Don't know, okay, any stereochemistry involved in this one. So this is just a simple reduction reaction. So the reason that this is not because they have did the reduction of this ketone as well with this H2PDC. Okay, the next question. So this is the another question. So which involve the elimination reaction, I think. So we have the starting material with this hydroxide here, MOM here, and we have added sodium hydride plus CS2 and then methyl iodide. So where the reaction occurs. So if you go one step by step, sodium hydride is source of H minus. If you look at the reactive center here, the OH, it will form O negative. And then if you treated this with the C double bond S, O negative attacks here. So we get basically this is what we get intermediate. S negative, and if you add the methyl iodide, so it will be O, I think like this, SCH3. Then we have the Bu3SNH and AIBN. So this is basically one of the Bu3SNH and AIBN. So how the reaction works on the center. So I think within this step, basically, this elimination occurs. We have here one hydrogen, and now this entire group is good living group. So this can eliminate in this fashion. So we get eliminated product like this, which has this group here. So this is what we get in the first step. And in the second step, sorry, here we have one methyl group like this. In the second step, what we have this Bu3SNH and AIBN in the benzene solvent and refluxed. I think this is the condition used for the deprotection of the MOM. So I'll just check the condition for the deprotection of this MOM group. Okay, this is not the condition because to deprotect this MOM group, we need to use the TFA. So definitely not the reaction condition. U3SNH tin hydride. Tin hydride is the source of hydrogen, but it is the AIBN. Whenever we have the AIBN general reaction goes through the radical mechanism. So I think all these two steps are involved in the first step up to here, and then elimination of this entire step, entire group, and passing this hydride to here. So basically, instead of forming this double bond, so there might be the addition of these hydrogen. So the most possible answers with these reactions are the one which has this hydrogen attached, which comes from this AIBN, sorry, which comes from this Bu3SNH. The other possibility is, so it can form initially the double bond and then the reduction of the double bond using this Bu3SNH and AIBN. So either both way it can go. I mean, one of the way it can go to get this compound D as a product. So we need to check that one. Actually, I'm also new to these conditions. What the reaction condition they have used to get this problem, this target molecule. The next question, next series, next step on the same material is the for the reaction of this the target molecule that sorry the molecule that the option D on that one this H2SO4 and acetone. So basically this just did the MOM deprotection. So which get converted into the corresponding alcohol in the first step, and then this is the chromic acid pyridine. So basically the oxidation of this double bond, so which leads to the formation of this. So the first step gives the formation of the starting B, and upon reaction upon this second step, we can basically get this oxidation of this. So we get a product in these two steps reaction. Whatever problems we are not able to solve here, as in the last problem, you should refer back the original article in that one and need to look at the reason they have given to form this product. You need to identify that one. Okay, in this case, these two steps are quite straightforward. So in case of acid, so this mom the production steps occur, and the next step is the reaction of this alcohol from with the styrene reagent. So which leads to the formation of compound A. So we have this as a product. Then if you treated this product, so the last series of last step in the same uh, product form, which is okay. So this step, so conversion of this to this. So what you will gonna use to get this one? So what we have here, the ketone, and we know the reaction of a ketone with the Wittig salt. What we get? Um, we get the olefin. So I think Wittig reaction also we have covered once. So we have this Wittig. If you treat it with this E, sorry, CH2 negative, PPH3 positive. Sorry, not this one. Uh, I will just write down in the form of their positive and I negative. So this Wittig salt. So basically, this is the one. So butyl lithium is used to, sorry, the base abstract these protons CH3. So it will form the intermediate CH2 double bond P PH3, and this Wittig salt basically is used on this ketone. So it leads to the formation of this CH2 product. So option C here is the, it seems most relevant here. The other option, if you look at here, the PPHC CBr4, so it will lead to the formation of CBr like this product. Another here given is the CHOCH3. So basically, this is not the good Wittig reagent. Then other option here is CH2I2, then zinc copper couple. So basically, this CH2I2 when it treated with the, I think this is this is one of the name reaction. So reaction of the olefin with this CH2I2. I forgot the name actually for this one. So it shows the some CH2 I. So like this butterfly mechanism. But obviously in this case, this is not the correct answer. Options. So option C is the correct option here. So this is about the some problems from the assignment 12. So they are basically one article, just professor have just given that divided into the individual steps just to get the correct, just to know. So if you look at all the answers, you can find out this is the one of the synthesis, stepwise synthesis that is mentioned here. And this is how generally the synthesis work. If I just show one of the example from my work actually, so you can understand the how the synthesis is generally can be done. So I will give one some examples here, which is actually originated from one of my paper. Okay. Yeah, I will give this. Okay, so this is the synthetic route for these two materials. I'll just explain it quickly to you. Okay, so I want to synthesize these molecules. So if you look at this molecule, uh, what you can see in this molecule, we have here the central one linker with these carbazole parts attached on the both side. So how I have did the synthesis of this molecule. So to synthesize this molecule, I have started my synthesis with the this acid. So this acid when treated with the acyl chloride, so when we treated this acid with the SOCl2, what happened? It will convert into corresponding acyl chloride. So this is the first step, individual step if you look at the acyl to acyl chloride conversion. The second step is treating this acyl chloride with the third butyl benzene like this benzene. So what happened? If you have heard the name, the Friedel-Crafts acylation reaction. So acyl chloride plus AlCl3. What happened? Acyl plus AlCl3, acyl chloride plus AlCl3, and the benzene. So in this case, terbital benzene. So it will show the acylation reaction, right? So it will be acylation reaction, and it works at the ortho or the para position, right? To the electron rich group. So in this case, electrons, the donating group is third butyl group attached on this benzene. So ortho position is sterically less reactive than the para position. So therefore, we get selectively this para acylation product. So this is what product we get in the acylation reaction. Then I did the second fragment synthesize. So I have this available fluorobromobenzene. I have coupled this fluorobromobenzene with the carbazole. So let's say we have this carbazole in place of the base cesium carbonate, the reaction that I mentioned earlier. So this carbazole shows selective reactivity toward this fluorine center. So ipso substitution reaction occurs here. So we get this bromo compound here, as you can see. The step involved here is the nucleophilic aromatic substitution reaction. Then I have converted this bromo to corresponding boronic ester. So the reagent that I have used this bisphenol diboron. So this is common Miura borylation reaction. So it generally occurs in the presence of palladium catalyst and the bisphenol diboron. We need to use some base. Here I have used the potassium acetate. So I got this boronate ester, and then I have coupled this boronate ester with this dibromo compound. So this is the compound, this compound with this compound, and this boron ester using Suzuki coupling reaction. So what is the condition for Suzuki coupling? So the palladium catalyst, the base. So here I use palladium catalyst as a palladium DPPF core. The base I use here the K2CO3. Solvent I use water, toluene, and T-butanol. So this is combination of solvent. I use all these solvent together in 1:1:1 ratio. And in this coupling reaction, I got so this boric ester get coupled with this phenyl ring by substituting this bromo functionality. So I got this intermediate. So then what I did, I treated this intermediate with the 1-bromobenzene and butyl lithium. So basically, I will mention here. So if I have this bromobenzene, here actually the T-butyl substituted. So bromo plus butyl lithium, what happen? So it will convert into the phenyl lithium, right? So basically here we get the negative charge and Li plus lithiation basically. So the lithiation reaction occurs within this two reagent, and then this two reagent attacks on this, what happen? So basically we get this phenyl negatively charged here. So it attacks on this keto and both these keto functionality. So here on the top side we have one keto and on bottom side another. So we get this compound get converted into the corresponding alcohol. And then if you add the BF3 thread on this alcohol, what happen? So if you react this alcohol with the BF3 thread, so this O BF2, right? So this become good leaving group and potentially eliminate. So we get carbocation, tertiary carbocation at the center. So OH group entirely get eliminated. And at this position, what do we get? We get a cation on this carbon center. Further, what happened? So this ortho position of this benzene attacks on this position, the cation form. So we get here the target molecule. So basically, so how many reaction steps involved in the synthesis of this molecule? The first step is acylation, then the first step is the acyl formation, Second step is the Friedel-Crafts acylation reaction. In this side, the third step is the aromatic nucleophilic substitution reaction. Here, fourth step is the Miura borylation reaction. Here, the sixth step is the Suzuki coupling reaction. The seventh step is addition of the nucleophile to the carbonyl center. So basically, it is a nucleophilic addition reaction. And in the eighth step, this is basically a aromatic electrophilic substitution reaction, because we are generating initially electrophile by addition of this BF3 on this alcohol. So alcohol become good leaving group and potentially eliminate and form carbocation at this carbon center here. So on this carbon center, this aromatic shows aromatic substitution reaction, and we get the target molecule. So this is how several steps are involved in synthesis of one molecule. So in the same manner, professor has also given various steps in the assignment. So all the steps belong to one synthesis of the molecule, and still this is the intermediate. This is not the final molecule, S- because some other steps may also involve to get final desired target molecule. So this is how you can approach the solving the various synthesis. So we'll stop here for today. So do you guys have any doubt regarding what we have discussed today? Except few questions, we are not able to identify proper mechanism to solve the questions. I also need to refer back the original article, original research paper for this reaction condition. So they are not very trivial reaction condition. But yeah, in this way you can basically do the synthesis of the molecules. So any doubt? We'll stop here for today, and maybe we'll take some more real life examples in the next session. Actually, we haven't really solved the problem that I have to covered. I will just share the screen on these the one PDF that I had. So yeah, so this is the one PDF. I will upload that PDF in the OneDrive, so you can refer back that one and try to get solve all these problems. So they are all very simple problems. So I will upload this PDF. It's only a 15-page PDF, so have around 20 to 30 examples. Just refer these examples, so it will be easy for you to understand some more detail. I will upload this in the OneDrive. So do you guys have the link for the OneDrive to download the PPT and the the reference book that I provided?
Can you please share again the link?
Yeah, I will share the link actually, so it will be easy for you to just keep the link saved. So, okay, okay, I have shared the link in the chat box. Please keep that link saved. I will upload the some more reference book and some PDF which involve the problems which have the on this retrosynthesis. So there are some books which are I think will be quite helpful for you guys. So maybe the Nance, I will upload that one. You have the I will upload the Claydon, also McMurray Organic Chemistry 8th edition. So I will upload this reference book in the same folder, so you can download that one and keep save for your future reading. Okay. So have you saved the link? So we'll stop here for today. Maybe uh, come back on the next video. Maybe the video will be the last for the next week. That will be the last session. So if you guys want any book in the form of PDF, just uh, let me know. I will try to get it available. Otherwise, you there are several online resources you can download from that one. So thank you.